Hi everyone, I'm Jia Zhao from Simon Fraser University. I will talk about our work toward scalable backscatter sensor mesh with decodable relay and distributed excitation. This is a joint work with Dr. Wei Gong and Professor Jiangchuan Liu. Sensor networks usually work as front end of Internet of Things for large-scale sensing deployment in agriculture, field, industry, or smart city environments. What has long been considered is how to build lightweight nodes so that their operational overhead can be significantly reduced. Lightweight design is a fundamental challenge because it has to deal with so many trade-offs among transmission, computing, and power supply. What has happened and will happen to individual sensors is to decouple computing and energy source from communication. This can be seen from today's edge or cloud-empowered IoT design that offload nearly all the computing tasks from end sensors to some high-performance sync node, whereas sensors in this architecture can focus on communication and get rid of complex hardware from data processing. For another couple, we have the backscatter technology that can decouple the energy source from the information source. Our previous work extends this approach to a multi-hop scenario, but has a limitation that the excitation must happen to the initial hop, no matter how many nodes there are across a transmission path. This is a centralized mode that cannot decouple the position of ambient energy. The excitation is centralized because the backscatter sensor cannot decode their previous hop data when they are doing relay for each other. Even if there are available excitations nearby, it cannot be used. Experiment shows that the multi-hop backscatter signal strength drops quickly as hop count increase. This signal attenuation is caused by multiple times of backscattering, just like the signal is reflected multiple times by blocks. Multiple sensors can only use the first hop excitation for multi-hop backscatter communication. If the second or third hop sensor moves away from the excitation source, its backscatter signal will attenuate rapidly. Such an excitation mode is caused by the non-decodable backscatter relay. It cannot decode the information from a high-frequency backscatter signal that comes from its previous hop sensor. So it is not unable to modulate the information on its nearby excitation signal. Since backscatter communication cannot embed modulated carrier onto a new high-frequency excitation, what a non-decodable forwarding does is to reflect the modulated carrier entirely without any change, or directly use the modulated carrier as its excitation signal. Because the modulated carrier has been reflected multiple times by previous hop sensors, its signal strength would be too weak to be backscattered again. Then multi-hop signal will attenuate rapidly and directly lead to the limitations on hop count, sensor-to-sensor distance, and multi-hop throughput. Our solution is to change this centralized excitation mode and decouple the position of ambient energy so that the energy supply can happen at any physical position if necessary. To do this, we need a decodable backscatter relay. It can first decode its previous hop data and then backscatter the next hop with a nearby energy source. This change will lead to a scalable backscatter sensor mesh Compared with the centralized mode, decoupled decodable relay and distributed excitation can largely extend the sensor network coverage and get high throughput and robust connections. Our key design is a backscatter sensor architecture that includes two data paths. The sensing path collects sensor data and generates a baseband using amplitude modulation. The relay path enables a sensor to decode its previous hop sensor's baseband signal and forward it to the next hop. To build a sensing path, we have to first make sure that the sensing paths are free to connect with external digital sensors. And we also need to decode a wide range of data that comes from diverse applications, from scalar sensing to multimedia sensing. Both challenges need a deliberate baseband design. Our solution is a front end that can generate both digital and analog baseband. The digital sensing front end connects external sensors with analog to digital device or FPGA drive circuit that can convert sensor output into a bit stream for modulation. It can generate a baseband that uses binary amplitude to represent digital data. The analog front end uses discrete components and analog sensing components such as thermistor, photoresistor, and microphone, corresponding to the analog readout for temperature, light, and sound. We use a pulse width modulation circuit to generate an analog baseband. The design of a relay path also have several trade-offs. Since previous hop baseband can be either a digital signal or an analog signal, a backscatter sensor should be able to decode them both. And such a decodable relay should not add much power consumption to a backscatter sensor. We also have to deal with the poor signal strength for amplitude modulated signals. Our solution is to enable an amplitude demodulation in the backscatter sensor with envelope detection. We use a double diode detector circuit that can down-convert to baseband to get a binary amplitude or pulse width signal. Since the previous hop signal strength is out of the sensitivity range, we use an aggregation node to assist the detector and perform an indirect decoding. The aggregation node can first demodulate the sensor's baseband signal and then use active transmission that can provide sufficient strength for envelope detection. Another way is to use a log ratio function component to perform multi-antenna decoding. This is a direct decoding that can eliminate the aggregation node but has to trade off the distance between two sensors. Each stack rail sensor can do sensing and relaying simultaneously. We backscatter sensing data and relaying data to two different frequencies so that there is no interference between these two types of data. We built a DAC rail sensor prototype using an FPGA, discrete component, and off-the-shelf IC devices. The analog components include the digital and analog sensing and baseband circuit, a double diode envelope detector circuit, and a multi-stage power detector circuit. This figure shows the modulation circuit For analog data modulation, we exclusive or an analog baseband signal and a frequency shift clock signal to generate output that can directly control the RF switch. Analog data modulation can only use single tone excitation. It starts backscattering by synchronizing to the positive edge of the first detective pulse. For digital data modulation, we use a counter block and a D-type flip-flops to generate a symbol duration. When using Wi-Fi excitation, we use an external power detector to synchronize to the beginning of Wi-Fi excitation packets. We use FPGA's internal clock and frequency division circuit to generate 10 MHz and 20 MHz signals. Then we use a multiplexer to select between the two signals for different frequency shifts. We use an 8-bit control message to reconfigure a Decouple sensor. This figure shows the FPGA logic that can interpret the control message and switch on or off the decodable relay and switch between different baseband types. We use power monitor to measure the PCB power consumption, and we use Cadence IC design platform to do power simulation. Our result shows that the Decouple sensor consumes 337.9 microwatts of power using IC design. We evaluate Decouple multi-hop system in a field experiment with different configurations. Compared with previous work, X-tandem Decouple largely improves signal quality and extends the last hop communication range to 20 meters. Multi-hop backscatter communication range can be defined as the maximum distance between the first hop sensor to the reader, which equals to the sum of multiple sensor-to-sensor distance and the last hop sensor-to-reader distance. The communication range of X-tandem is limited for two main reasons. First, X-tandem tags are non-decodable and only use the first hop excitation, whose transmitter power already decides coverage. Second, X-tandem's tag-to-tag distance is up to 40 centimeters, which is ignorable compared with its last hop distance. Differing from X-tandem, each Decouple sensor can utilize a new excitation with good signal strength and hence minimize the impact of multi-hop signal attenuation. For digital baseband modulation, Decouple also increased the multi-hop throughput to 40 kilobit per second, which is 200 times more than the throughput of X-tandem. Decouple also improves the bit error rate, but each hop's bit error will impact the next hop, so the bit error rate increases with the hop count. Wi-Fi excitation has large communication scope than single-tone excitation, but the peak throughput of single-tone excitation is higher than that of Wi-Fi excitation. And single-tone excitation can be used for any hop, while Wi-Fi excitation can only be used for the last hop communication. Decouple sensor-to-sensor distance can be up to 48 meters, 4.8 meters, which is 10 times more than the performance of X-tandem. Decouple can backscatter audio data with a sample rate of up to 48 kilohertz. And the multi-hop sensor achieves similar signal quality for both sensing and relying communication. In the future work, we will focus on some limitations of our current implementation. For example, it only supports commercial radio excitation in the last hop. To make full use of available ambient radios such as smartphones and access points, we need to add more complex on-tech decoding functions or pluggable RFID readers for smartphones. The aggregation node is also possible to be eliminated using the multi-antenna decoding with a trade-off between throughput and sensor-to-sensor distance. For concurrent relying requests, our implementation uses the control message to notify tag to process the request one by one. For large-scale networks, a more efficient way would be a network protocol and a sensor state machine to coordinate the request. To summarize, we have built a backscatter system that can fully utilize distributed excitation to reduce multi-hop signal attenuation. And we demonstrate that decorative sensor can perform decoupled relay simultaneously with multimedia sensing. We hope this is the first step towards building a low power and high performance sensor mesh networks.